Well, good afternoon. My name is Sinan and I'll be talking about how distributed monitoring helps us understand the response of masonry arch bridges. And to illustrate my points, I will use a case study from London Bridge Station Redevelopment Project. Most of my colleagues today talked about monitoring new structures, but we also, here at CSIC, we also work on old structures, existing assets. And currently 40% of the country's bridges are masonry arch bridges. And generally masonry arch bridges are beautiful structures. They last quite a long time, but they can degrade, which is the issue we have to deal with. But fortunately, as engineers, we've developed a good understanding of how they respond. For instance, when a masonry arch settles, we know it formulates hinges and we know it cracks. And we also know its long-term response. We broadly understand its long-term response, which is affected by rail loads and water ingress. But despite all this information, we still have difficulties. It is extremely difficult to predict the settlement and dynamic response of these structures. The crux of the issue here is that we've got heterogeneous material that we have to model. We need to include existing defects in the structure, and all this aspect makes modeling difficult and unreliable. So in London Bridge Station Redevelopment Project, engineers had to deal with all of these issues. And they had to, piles were going into historic arches, and movements had to be controlled because trains were running above. But settlements due to piles were uncertain because of local geological differences. So when we engineers do not know something, we go around measure. And this is what was done. There were a number of total stations, an extensive monitoring network of a number of targets. And we could understand how things were moving, and we could compare that to several movement thresholds. But the difficulty here was understanding what the structure was doing, which is, again, it's composed of many millions of blocks. And also, because we didn't have enough detailed information, we need to estimate a way to get damage from the total station data. And we used a method that was used for masonry facades is often used. But again, the difficulty here is how do we relate damage to the monitoring data? And for masonry, we need more information. And I believe that more information can come from distributed sensing that we've explored in this project. We need to be able to be sensed almost all places on masonry so we could see where the mechanisms are developing. So we looked at this using fiber optics and laser scanning. Here's an arch that we instrumented with fiber optics, just a cross-section of it. We analyzed this data with brilliant optical time domain reflectometry. We got these nice plots. And when we got these nice plots, we noticed that actually, perhaps we can see cracks through these plots. And indeed, this is one thing that we hadn't planned for, but we could see without knowing where the cracks were occurring, we could see them because we were doing measurements on the surface. And considering how important that is for assessment of masonry, it's a traditional damage indicator, the crack, it was very useful. So we can now perhaps use this for long viaducts where we can also assess long-term response. And I believe distributed monitoring is useful for this purpose. And we also looked at the 3D movements of masonry arches. As I said, these are distributed structures, so we need a distributed understanding of how things move. On the bottom plot on the right, you see the vertical movements of the arch, and the blue sides are where the piles have gone in. And settlements were observed about 25-30 millimeters. Well, this is a nice color plot, but if we look at it in more detail, we could understand even further. And what we could understand from this extremely rich data was the two-hinge response mechanism of the arch. So we could quantify what was happening inside the arch all along, which is very useful, and then we could use this to calibrate computational models, which is useful for the next people who come in and analyze the structure, and which is useful for us. But it hasn't been all easy. To get useful data is an adventure. And cable slippage was an important issue. Our cables were slipping on some of the hooks, so we did some lab tests working on it. Another thing is with laser scanning, registration and comparing laser scans is a difficult thing, which we worked on. So all of it was a past. Now we're looking at new things, and this involves dynamic response of structures. We know that rail loads can cause degradation, and we'll be looking at dynamic distributed sensing, which hasn't been explored yet in any of our projects, and we're doing some lab tests on it at the moment, and then some video gauge technology, which is, again, giving us new opportunities. Last week, we saw these arches in Leeds. These arches, instead of being retrofitted, they were filled in with concrete and left as such. And I believe that distributed sensing can help us better understand these arches and can help us with better retrofit. We'd like to thank all of you for being here today, but we got a lot of support from Topcom, Costain, and Network Rail, and we'd like to thank them very much. And we hope this research will help our partners by improving the monitoring techniques, allowing safer construction, and reducing costs of managing existing assets. Well, thank you very much for coming.